D block elements. So what are D block elements? So as you know that the definition for the S block and P block, here it is the same one. So how can we call D block elements? So D block elements means these are the elements so in which the lost electron, that means the differentiate electron that enter into the D subset or D orbitals. So that elements are known as D block elements. D block elements means so these are the elements in which the differentiate electron enter into its D subshell or G orbital. So that elements are known as D block elements. So in the periodic table, the location for the D block elements means the D block elements are located in between the S and P blocks. If you see the periodic table, see this one. So this is a periodic table. So here the D block elements are located in between the. So these are the S orbital and these are the P block. These are the S block. Sorry, this one is S block and this P block. So D blocks are present in between the S block and P block elements. So let's see the properties of D block elements. So here are some properties. So in that the first one, so there is electron configurations. So let's see electron configuration for the D block elements. That means what are the elements that will show the different type of electron configurations, and why they show the different electron configurations when you compare with the other elements. So here the D block elements are majorly divided into 3D series, 4D series and 5D series, and that is the 6D series. So here is the 6D series is the incomplete series. Now here the 3D series, in the 3D series what are the elements are present? Scandium, titanium, iridium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So these are present in the 3D series, and these are the elements so that are present in the 4D series, and these are the 5D series, and this one the 6D. So that is the incomplete series, that is the block series. So when you see the electron configuration for the every series, so here it is the general electron configuration for the D block elements. Here it is n minus 1 D 1 to 10 and ns 1 to 2. So this is the general electron configuration for the D block elements. So what is that general electron configuration for the outermost D block elements? So that is n minus 1 D 1 to 10 and ns 1 to 2. So this is the general electron configuration for the G block elements. So if you see the period 4 electron configuration for the period 4, so there is beginning with the argon and 4s 1 to 2, 3d 1 to 10. So this is the electron configuration for the period 4, and coming to the period 5. So here it is the up to krypton the electron configuration will be same, and after that the outermost electron configuration it is 5s 1 to 2 and 4d 1 to 10. And likewise for the period 6 the electron configuration for the period 6, so there is xenon, so there is 0 group elements. So we know that up to xenon there is no change in the electron configuration. So after that the outermost electron configuration, so there is 4s 1 to 2 and 3d 1 to 10. So this is a general electron configuration for the G block elements, outermost elements. So here it is the important one. This one is n minus 1 D 1 to 10 and ns 1 to n 1 to 2. So see this one. So here it is the first and second and third transition series. Here it is. First transition series, so that is scandium, titanium, iridium, and scandium to zinc. So these are the outermost electron configuration for the first transition series. So here 4s2 3d1 to 4s2 3d10 series. So like that, second transition, so the elements are Cm2 cadmium, and third transition, so that is lanthanum to mercury. So if you observe the electron configuration for the block elements, so there are they will show the different type of electron configuration. So here's some we indicated with the different color. See this one, the chromium column. So here it is. They will show the different electron configuration. So when you observe the previous elements, so that will have the different electron configuration. So as well as the niobium and this one ruthenium, rhodium, and palladium, and also tungsten. So these are some elements will show the different type of electron configurations. So when you compare with the other d block elements, so then why these elements will show the different type of electron configurations? So here the main reason for the anomalous behavior for the elements which are shown the different type of electron configurations. So here it is the reason for that, the energy gap between the ns and n minus 1, the gap that is between the ns orbital and the n minus 1 d orbital, that in some cases the energy gap between the are negligible. In some cases there may be more or there may be less. So because of that, they will show the different type of electrode, or they will have the different type of electron configurations. And another one, that is pairing energy. The pairing energy for the electrons in s orbitals, so that will also affects on the electron configurations. So, and the next one that is important one, the stability of, when you compare the stability of off field or full field with the partial field orbitals. So obviously there is a more stable orbitals in that case. So here there is off field orbitals have somewhat more stable than the partial filled d orbitals, as well as the full filled orbitals. So that means for example, if you see some d10, and also off field means d5. So d5 it is more stable than the d1, 2, 3, 4. So like that. And also the fulfill, as we know that a fulfill d orbitals will have the more stable than any other d configurations. So here is series one. Off field it is also a more stable configurations. So that is when you compare with the other 1, 2, 3, 4 configurations. So d5. So this is a off field d orbitals are very much stable than the 1, 2, 3, 4, and also the full-filled d orbital configurations also stable. So these are the some factors that affects on the electron configuration. So these are the factors. So there are reason for the those elements which are the different type of electron configurations with the other d block elements. So what is that? The energy gap that is between the present ns orbital and n minus 1 d orbitals. And next one, the pairing energy, the electrons which are present in the ns orbitals, and also the stability of the off field and fill field. They have more stable than the remaining G configurations elements. So that is why they will show the different type of electron configuration. So if you see if you observe the chromium, if you observe the chromium electron configuration, so the outermost electron configuration, it will present as a 4s2. It must be present 4s2 3d4 as per the theory, 4s2 3d4. But practically the chromium will not having this configuration. So that is 4s2 3d4. Instead of that, they will show the configuration. So that is chromium has the configuration 4s1 3d5. So in this configuration, if you see this one, 4s2 3d4, and another one that is 4s1 3d5. See this one. If you observe these two configurations, so you will understand what is the why the chromium will show the different electron configurations. So here, when you observe the d orbitals, so here the d configuration is d4, and another one is d4. See, d5. So which one will have the most stable? Yes, obviously we know that the d5 configuration is the most stable than d4. So why? Because see this one, the d5 means it is a upper field. So it is off field configuration. So d4 means it is a partial field configurations. So based on the stability of the G configuration, so here it is the d5 configuration. That means the half field configuration is the most stable than the remaining partial d orbital configuration. So that is why the electrons, which is uh, the differential electrons, enter into the d orbitals instead of that s orbital. So the same theory will apply to the copper. When you see the copper configurations, so as per our knowledge, that the copper must be show this configuration. So there is 4s2 3d9. So this is the outermost configuration. But practically, what happened? What is the electron configuration for the copper? So here it is. This is the electron configuration for the copper. So that is 4s1 and 3d10. So why? Because here it is the 3d10 and 3d9 orbitals are there. So as per our knowledge, which orbitals will have the more stable? Yes, we know that full filled orbitals have the more stable than the partial filled G orbitals. So based on that, the copper will show the electron configuration for electron configuration. So there is 4s1 3d10. And also coming to the second series, so what happened in the second series, some of the elements will show the different electron configuration. So that is after the niobium, from the niobium, the elements which are present from the niobium, so that will show the some different electron configuration if you observe the periodic table. So that is because of the S and D orbitals have the almost the same energy. So due to this one, the elements which are coming from the niobium, so that elements will show the some different type of electron configuration. So that is why the s orbitals has mostly one electron. So one electron is only present in the s orbitals. The elements which are coming from the niobium onwards, so that will have the only one electron in the s orbitals. So this is because of the s and d orbitals of the almost the same energy. See this, the s and d orbitals are almost the same energy, having the same energy. So due to this one, in the second series, so most of the elements containing one electron in the s orbital. So coming to the next series, so that is third series. So in the third series, some of the elements will show the different type of electron configuration. So this is because of the pairing energy. Here it is due to the pairing energy, the electron pairing energy, they will show the different type of electron configurations. So here it is. See this one, for example, if you see the electron configuration in the third series, so there is tungsten. So W will show the electron configurations. So there is 6s2 5d4. Yes, you have one doubt, sir. The remaining elements, so that is 6s1 5d5. If it is present like this, then why tungsten will not show this type of electron configuration? So here more pairing S configuration even at the expense of off-field orbitals. That means the more pairing energy, it is the overcome to the off-field orbitals. If the tungsten having this off-field configuration, so this is a very unstable when you compare with this configuration. So in the tungsten, so coming to the tungsten will show only this configuration, but not this one. So this is because of the pairing energy, it is a overcome to the off-field orbitals. So that is why tungsten will show the 6s2 5d4 electron configuration instead of that 6s1 5d5. Even though in this configuration presence of off-field deconfiguration, but here it is what happened. The pairing energy it is the more effective on the tungsten elements than the that off-field electron configuration. So that is why tungsten will show the 6s2 5d4 rather than the 6s1 5d5. So remember this one. And also one of the thing is that is lanthanide contractions. Due to presence of lanthanide contractions in this series, they will show the different type of electron configurations. So that is about the electron configuration. So the next property of the d block elements. So there is variable oxidation states. Variable oxidation states. So then why d block elements will show the different type of oxidation states? The d block elements will show the different type of oxidation states instead of the one oxidation state. So this is because of the energy between the s and d orbitals are very small, and the d electrons as well as the s electrons are also participants are involving in the bond formation. So that is why the d block elements will show the different, that means the variable valency or variable oxidation states. So why the d block elements will show the different type of that means the variable oxidation state, that means more than one oxidation states they will show. So that is because of the s and d orbitals, the energy between the s and d orbitals must be s or small, and also the electrons which are present in s as well as d both are involving in the bond formations. So because of this one, the d block elements will having more than one oxidation states. See this one, in these d block elements the minimum oxidations arise by losing the s electrons. See this. The maximum oxidation states, so that is the equivalent to the total number of electrons available in the both the s and d orbitals. If the d, see this one, if the d block elements, the s orbitals of the d block elements will only involve in the bond formation, then that time the d block elements having the minimum oxidation state. So when the d block in the d orbital electrons and also s orbital electrons will involving in the bond formation, so in that situation they will show the maximum oxidation state. So here is the 3D series, that is 3D series. So these are the elements present in the 3D series: scandium to zinc, and these are the outermost their electron configurations, and these are the possible oxidations for the 3D series. So once you observe this one, you can understand. So the scandium will show the only plus oxidation state. The plus oxidation state means, So in this scandium element, the electrons which are present S and D, both the S and D electrons are involved in the bond formation. So that is why they will show the +3 configurations. So in the 3D series, the minimum, that means the lowest oxidation state is the +1. The highest oxidation state in the 3D series, so that is +7, that will show the manganese. So observe this one. What is the minimum oxidation state in the 3D series? So that is +1. And what is the maximum oxidation state in the 3D series? So that is +7. That should be shown by the manganese. Series 1, the scandium and zinc. Scandium and zinc, they both do not exhibit the variable oxidation states. That means the scandium and zinc will show only one oxidation state. So here it is, the scandium will show the plus oxidation state. That means in the plus oxidation state, if you observe the electron configurations of the scandium in the +3 configuration, +3 oxidation state, it is the most stable electron configuration. So as well as here it is the zinc. When you observe the zinc will show only +2 oxidation state. In the +2 oxidation state, the zinc will have a stable electron configuration. So there is this one, organ and 3D series. The completely filled d orbitals are present. So here also the 3s2 3p6, the complete filled orbitals are there in the +3 state of scandium and also +2 state of the zinc. And the all elements of the first transition state series, the except scandium state, they will show the oxidation state +2. Except scandium, all elements in the 3D series, that means first series, they will show the oxidation state. So that is +2. And also they will show the +3 oxidation state also. Except zinc, all the elements will show the +3 configuration. Except scandium, all the elements will show the +2 configurations. Yes, we know that the highest configuration is shown by the manganese in the first transition. So there is a 3D transition. So there is +7. So +7 configuration will present in the manganese oxide compound. See this one. In these compounds, the manganese will show the +7 configuration. So these are the best example for the manganese compounds. So in where the manganese will show the +7 oxidation state. So in that case, that means if you observe the manganese compounds, the +7 means 7 electrons removed from the, as per our knowledge, +7 means from the manganese 7 electrons. When you remove the 7 electrons from the manganese, then they will show the +7 oxidation. So this is our knowledge. But here it is +7 means manganese does not mean that all 3D and 4s electrons are removed from the manganese to give the manganese +7 series. So instead of that, the manganese form the covalent bonds. Manganese form the covalent bonds with the oxygen atoms by making use of its off-field orbitals. Then this way, the manganese will show the +7 oxidation state instead of the removing the all electrons which are present in the d and s orbital. So remember this one. Manganese will show the +7 oxidation state. That means not mean that all the 3D and 4s electrons remove from that. Instead of that, manganese will form the covalent bonds with the oxygen with it off-field orbitals. So remember this one. So in such a way, the manganese will show the +7 oxidation state. If you observe the structures of the manganese compounds, see this one. This is M1O4 -2. In this case, the manganese will show the +7 oxidation state series 1, 2, 3, 4, 5, 6, 7. In this compound also manganese oxide, this is Mn2O7. In this compound also manganese will show the +7 oxidation state by forming the covalent bonds with the oxygen series. So for the elements of the manganese, so there is a reduction in the number of possible oxidation states. So yes, we know that after the manganese, automatically there is a decreasing in the oxidation state. So if you observe that variable oxidation state table in the previous series, it is this one. So in this case, what happened after the manganese? After the manganese, there will be decreasing in the oxidation states from the top to bottom. Manganese to zinc, there will be decreasing in the oxidation state. So that is because of the decreasing number of unpaired electrons and also the increasing in the nuclear charge. So due to the decreasing in the unpaired electrons from the manganese to zinc, and also due to increasing in the nuclear charge from the manganese to zinc, they will show the there will be a decreasing in the oxidation states. And if you observe the next series, so that is yttrium to cadmium. So these are the possible variable oxidation states of the 4D series 1, yttrium 2 and cadmium. So in this case, the minimum oxidation state is the +1, and the maximum oxidation state in the 4D series, so that is +8. So that will showed by the ruthenium series. So this is 4D series. So coming to the 5D series, so this is the 5D series. In the 5D series, what are the elements of presence? Lanthanum to mercury. So in this series, the minimum oxidation state here it is the +1, and the maximum oxidation state in this 5D series, so that is +8. So remember this one. And the 4D series, what is that? +1 and also the +8. Here also the 5D series +1, it is the minimum oxidation state. And what is the highest oxidation state in the 5D series? So that is the +8. That is showed by the osmium series 1. In this case, osmium. In this case, in the 4D series, so that is ruthenium. Ruthenium will show the +8 configuration, +8 oxidation states. Sorry, and osmium will show the highest oxidation state in the 5D series.